Okay, guys, so we're going to go ahead and go over section 9-1, which is a short lesson for us starting chapter 9. Chapter 9 is going to deal with differential equations and some different things that we can do with differential equations. So today's lesson is going to be dealing with modeling with differential equations. And let's take a look at some things that we've already talked about in regards to differential equations in this class, and we'll talk kind of about like how we're going to proceed with things as we move through chapter 9. Okay, so we've already looked at differential equations like the one we have listed here, where dy over dx is equal to x cubed. And we've looked at how if we start with a differential equation, we can use the antiderivative to find the function whose derivative is x cubed. So we know that when we take the antiderivative of dy over dx, the antiderivative of that is just going to be y. And we know the antiderivative of x cubed is x to the fourth power divided by 4. And then we add a constant c to the end. Okay. Now, when we find the solution to this differential equation, this is what is called the general form of the solution to the differential equation. Okay, so that is how we take the antiderivative of a function. We're going to learn of another technique in this section, or not in this section, but in this chapter called integration by separation of variables, which to us is going to be like the inverse process of implicit differentiation. And I'll show you kind of the basics of what that entails in a minute. But that's something that we're going to look at in a lot more detail when we get into section 9-3. But basically, the way integration by separation of variables works is you're going to start with your differential equation. Dy over dx is equal to x cubed. And we are going to integrate by separation of variables, which means we want to move everything that has the variable x in it to one side of our equation and everything that has the variable y in it to the other side. Okay, so for me to do that here, I'm going to multiply both sides by dx. So that gives me dy is equal to x cubed dx. And then we are going to integrate both sides of this equation. Okay, so when we integrate dy, that's like integrating the constant 1 with respect to y. So the antiderivative of 1 with respect to y is y. And then on the right-hand side, when we integrate x cubed with respect to x, the antiderivative of x cubed is x to the fourth divided by 4 plus the constant c. Okay, so that gives us another way to find the general form of the solution to that particular differential equation. Okay, so how we're going to use integration by separation of variables is when we have a derivative that is written both in terms of x and y. Okay, so we're going to see later on that this is what is called a separable equation. And separable equations are those in which we can write the derivative as a product of functions x and y. Okay, and we solve these separable differential equations by that process that we just went over, integration by separation of variables. Now, I'm not going to work this all the way through to completion. We're going to save that again whenever we get into section 9-3. but I just want to talk about that briefly now. So, and just get the problem started. So if we wanted to separate our variables, we could divide both sides of our equation by y, and we get 1 over y dy. We can multiply both sides of our equation by dx, and we get x cubed dx. And then once we've done that, we can integrate both sides of our equation. Okay, so if we take the integral of the left-hand side, that would give us the natural log of the absolute value of y. When we integrate the right-hand side, we get x to the 4th power over 4. Now, realistically, we would add like constants to both antiderivatives, but how we typically like work through this is we only add a constant to our antiderivative on the right-hand side, because I could have combined those two constants to make a single constant. Okay, and then we would just, to finish solving the separable equation, all we would wind up doing is isolating y on the left-hand side of our equation. Okay, so we'll work through problems like this all the way out to completion later on in chapter 9. Okay, let's revisit one other thing that we looked at earlier in the school year. Like way back in our first section that we went over in quarter 1, where this example asks us to find the particular solution to the differential equation with the given initial condition. Okay, so we have dy over dx equal to x cubed. This time we are given the initial condition where y of 0 is equal to 4. And if we recall, a problem like this is what is called an IVP, or an initial value problem. Okay, and for us, like whenever we have an initial value problem, it's going to allow us to find a particular value for the constant c that is going to be a solution to the differential equation that we are given and satisfies the initial condition that we are given. Okay, so if we work through this IVP, we know that when we take the antiderivative of dy over dx, that gives us y. The antiderivative of x cubed is x to the 4th power over 4 plus the constant c. And then we can plug that initial condition in to find the particular value for c. So when we do that, we have y of 0, which is equal to 4. When we plug 0 in the place of x, we get essentially 0 plus c, which makes the value of c 4. And that makes the solution to this differential equation x to the 4th power over 4 plus 4. Okay, so when we have an IVP like this, we are going to have a single function that satisfies the differential equation and the initial condition, where if we just have a normal differential equation, we're going to get a family of functions that differ by the value of the constant c. Okay, so we're just going to do 2 more examples to wrap this up. Directions for the next example ask us to show that the function y, which is equal to x minus x to the negative 1 power, is a solution to the differential equation 2x minus y is equal to x y prime. Okay, so what I'm going to do to start this one out is I'm going to go ahead and take the function y, which is equal to x minus x to the negative 1 power, which I can also rewrite as like x minus 1 over x. And I'm going to go ahead and take the derivative of that function. Okay, so y prime, whenever I differentiate that function, the derivative of x is 1, minus the derivative of x to the negative 1 power is negative 1 times x raised to the negative 2 power, which is going to, whenever I simplify y prime, give me y prime is equal to 1 plus x to the negative 2 power is 1 over x squared. Okay, so if I want to show that y is a solution to the differential equation, what I'm going to do is I'm going to take 2x minus y, and I am going to algebraically manipulate that expression to show that it gives me the right-hand side of that equation. Okay, so we're going to take the left-hand side, we're going to use some algebra to manipulate it and show that it gives us the expression on the right-hand side. Okay, so when we take 2x minus y, this is going to become 2x minus the function y, which is x minus x raised to the negative 1 power. So when I distribute the negative across both terms, we get 2x minus x plus x raised to the negative 1 power. All right, when I combine like terms, 2x minus x gives me x plus x raised to the negative 1 power. And then I want to make that expression on the left-hand side equivalent to x times y prime. Okay, so what I want to do is I want to somehow like take that expression and rewrite it where I get x times something. Okay, so that means that I can factor an x out of both of those terms. So what times x gives me x? Well, that's 1 plus what times x gives me x to the negative 1 power, or 1 over x, and that is 1 over x squared. And then once we've done that, we know that 1 plus 1 over x squared is equivalent to y prime. So I can replace that quantity in parentheses with y prime. So we've shown then that 2x minus y is equivalent to xy prime. Okay, so that function y is a solution to the given differential equation. All right, on to the last example. Okay, so the last example states for what value of k does y, the function y is equal to e times k, e raised to the kx power satisfy the differential equation 2y double prime plus y prime minus y is equal to 0. Okay, so what we're going to do for this one is we're going to start with the function y is equal to e raised to the kx power. And let's go ahead and take the first two derivatives of that function. Okay, so y prime, I have to use chain rule to differentiate e raised to the kx power. So the derivative of that is e raised to the kx power times the derivative of the exponent, which is k. So y prime becomes k times e raised to the kx power. And if I want to find y double prime, I can pull k out front. The derivative of e raised to the kx power is e raised to the kx power times the derivative of the exponent k. So when we multiply that times k, that makes the factor out front k squared. Okay, so once we know the values of y, y prime, and y double prime, we can go ahead and plug those values into our differential equation. Okay, so that's going to give me 2 times k squared times e raised to the kx power plus k times e raised to the kx power minus y, which is e raised to the kx power, is equal to 0. And then when we look at that, like, it's an exponential equation, but it's in a quadratic form. So we're going to go ahead and factor out e raised to the kx power. And when we do so, that gives us 2k squared plus k minus 1. And that product has to be equal to 0. Okay, so that quadratic factor is factorable for us. That's going to factor to 2k minus 1 times k plus 1. Now we know that this exponential function, that is never going to be equal to 0. Okay, that function has a horizontal asymptote at y is equal to 0. That function is never going to be 0, and it's also never going to be negative. Okay, so the only way that that product can be equal to 0 is when the first factor, 2k minus 1, is 0, or the second factor, k plus 1, is 0. And that happens when k is equal to 1/2 and k is equal to -1, respectively. Okay, so those are your two solutions to that differential equation. Okay, so guys, that's it. That wraps up 9-1, which is by far the shortest lesson in Chapter 9. Okay, we will see you guys in class next time. Take care.